like what is it? It's not. Oh, we lied. It's not when the units don't really work out because you raise the diameter to the 2.63. That doesn't make sense, right? So it's not dimensionally correct. That's what it's not dimensionally correct. So this one is dimensionally correct and it's well known to work. So in SI units, this one doesn't change. But again, I don't even think that one did. Let's see. Oh, it did change. So that's how I know it's not dimensionally correct, because it has to change if you change the unit. So I focus on that Darcy-Weisbach model. So we'll do a quick example and run this through to calculate the head loss in water flowing through pipe. So again, this is the energy loss due to friction in feet or inches or centimeters or meters of elevation height. Friction factor, which is a function of something called the Reynolds number. The velocity of the water in the pipe, acceleration due to gravity, g, length of pipe, diameter of pipe. And it's really based on this Reynolds number approach, which is a ratio of the fluid velocity and diameter of the pipe to the fluid kinematic viscosity. So it's the velocity times the diameter divided by the kinematic viscosity. And you can use a Moody diagram, well-known hydraulic diagram, to determine what the friction factor is to get this. That'll help you get the Reynolds number. So here's a Moody diagram. You can look it up in a book. Okay. So the Moody diagram looks like this. It's Reynolds number along the bottom, right? So friction factor F. I was just a student.
Mike,
okay, and then these blue lines, these are different types of pipe. And you can classify a pipe based on its relative roughness, which is how rough is the interior of the surface. Oh, thank you. Okay, so these are different pipe roughnesses, and really plastic pipe and the like. They're all very smooth pipes. So this is the smoothness of the pipe. So this is the line you're working with. And, you calculate the Reynolds number, the velocity, diameter, kinematic viscosity is a constant. You say, oh, I have a Reynolds number of like 60,000, and I go up here. I hit the smooth pipeline, I go over, and it's 0.019.
Does this work?
It's working.
Is this working? We turn the volume down.
So that's how you calculate the friction factor. Or, it's not that complicated. You can just create a little table. And in this case, I assumed a smooth pipe, did a couple of Reynolds numbers, and I have a pick table for the friction factor. So again, you have to calculate the Reynolds number for your velocity, right? And then you read off the friction factor, and then you can calculate the head loss. So a quick example is, we'll say 200 feet, 4-inch PVC pipe with 100 gallons a minute in it. A couple constants, one for gravity, one for kinematic viscosity. You calculate the cross-sectional area of the pipe, so that's pi r squared, where r is in feet for 2 inches. So you have this area of the pipe. The velocity of water through the pipe is then the flow, 100 gallons a minute divided by the area, 0.08. Right? Change the units here, so I'm canceling out things, gallons, and I end up with feet per second. So in this case, 100 gallons a minute. And a 4-inch pipe with this area is 2.5 feet per second. Well, that's a little high, right? But it'll move the solids anyways. I typically would shoot for something lower. Then I calculate the Reynolds number, velocity, 2.54, diameter in feet, divided by kinematic viscosity, and I get a Reynolds number of 69,330. I go to the Moody diagram. I pick a friction factor off for this smooth-walled pipe at 69,000, 0.019. And then I use the head loss equation, Darcy-Weisbach. Friction factor, 0.019, velocity, 2.5, 2 times the gravitational acceleration constant times the length of the pipe, 200 feet, divided by the diameter, 0.33. And that says you need 1.1 feet of energy to make that water flow in a 4-inch pipe for 200. So if you had all that water in a pipe and it was flat, not much is going to happen. But if you raise one side 1.1 feet, then you get the 100 gallons a minute going through it. Okay? So that's a simple example for the head loss in pipe. But there's not just pipe in research systems, unless you're FERT's system and you don't have any pipe. Usually there's pipe and fittings and valves. And so you can modify the Darcy-Weisbach, and they do, the hydraulics folks do, they collapse the friction factor times L over D into K. I love this stuff. So the head loss is just the K factor times V squared over G. And typically we call this V squared over G the dynamic head. It's just a sort of sign of that. And then you can look up different K values for different types of fittings. Right? This is from a very famous publication, Crane's Technical Pub. Gives you K values to use in that for various things. Unfortunately, that's a long time ago for iron pipe. And nowadays, we have more precise values for K from folks actually in the, still here, in the heating and chilling industry, because they tend to have higher velocities and they'll have smaller pipe or more fittings. So they're really interested in how the friction is in these coolant lines. Really? And so they hired this guy, Ray Meyer, at University of Idaho, and he did all these tests for pressure loss data on PVC plastic pipe. So you can look in his publications, and he'll have much more precise K values to use for different molded PVC or fabricated or mitered. So he's got all these K values you can use that you can then calculate the head loss using them. So in this case, we'll keep our 4-inch pipe at 100 gallons a minute, but we'll have 5 90-degree elbows. We want to know the head loss from the elbows. Again, calculate the area of the pipe. Hasn't changed. Velocity hasn't changed. It's still 2.5 feet per second. It's 100 gallons a minute in a 4-inch pipe. But we have 90s, and we look up from Ray Meyer's data. K is 0.91. And then we use the head loss for fittings. Is head loss equals K times the dynamic head, V squared over 2G. So K is 0.91, 2.54 squared divided by 2G, and you get the head loss is 0.091 feet per elbow, but there were 5 elbows, don't worry. And so the total head loss for fittings in this case is 0.46. So now we have some head loss in pipe, and now we have some head loss in fittings, but you can't design a research system with just pipe and fittings. You're going to need valves, right? And there's another set of equations that we have for calculating the head loss in valves. Typically, it's this CV-based approach. So the manufacturers of valves will have information for their types of valves, butterfly, ball, things like that, and they'll publish CV values. And you can use these CV values to figure out the head loss. And so the CV value is the gallons per minute that flow through a valve at a pressure difference of 1 psi. Okay? And if you have a flow and CV, you can determine the pressure, change your flow. So I'll show you how we do this. SI unit version of it right here, so change the units. So for example, this is a table from a manufacturer in the US of valves and pipe called Spears Manufacturing. This is their butterfly valve CV table. It actually gives you the CV value for different degrees of open, which is super important, and for different sizes. And you see this range of CV values in here. So just for example, we should take 4-inch pipe, 4-inch valve, butterfly, we'll say it's 100% open. That would be a CV value of 411. So what that means is 411 gallons a minute are able to flow through that valve with 1 psi of head. Fortunately, in this case, we're going to look at the 6 and the 8-inch. In this case, the 6-inch CV butterfly valve, fully open, processes 1,125 gallons a minute. But going up 2 inches to 8 inches in diameter essentially doubles the amount of flow for the same head loss. Remember, the head loss is 1 psi, hasn't changed. So there's a tremendous effect of valve size here that allows more flow at the same pressure. Okay, so we'll just do this example full out. So 8-inch butterfly valve, full open at 750 gallons